Okay, Wimmel. So before we resume with our program this afternoon, I just wanted to give you a quick reminder that as Wimmel attendees, you and all of the people around you have agreed to abide by our code of conduct that you can find at this link, wimmelworkshop.org/conduct. Our diversity and inclusion chairs that you've met this morning, Rachel and Sinead, are absolutely here to help you out with anything. So if you see anything, if anything happens, please report it to them or come find any of us organizers. We'll be happy to help you out. There are also all of the hotline phone numbers and email addresses that you can contact directly. Thank you. So we will actually start the program this afternoon with 2 contributed talks. Please welcome our first speaker.
Hi, I'm Mansi, and I'm going to speak about our ongoing work, learning to deceive with attention-based explanations, done with some awesome collaborators at CMU. So in the vanilla sequence-to-sequence model, one of the major limitations is that the entire encoder sequence has to be represented in a fixed size vector. And the attention mechanism tries to overcome this limitation. And the way that it does that, it computes a normalized weighted vector over the input space and uses that normalized weighted vector to predict an output. So this normalized weighted vector is often used by model developers to explain or justify the model's abilities and predictions. For instance, in so many varied tasks ranging from image captioning to entailment, document classification, and so on. But it is also sometimes used by evaluators to audit the models for bias and fairness, accountability, etc. So in some very high stake setting as well. So for instance, in this paper, bias in bios, the task is to predict occupation of a person given their biographies. So this paper assumes that the attention weights indicate which tokens are the most predictive. So we question this assumption and we ask, do the attention weights necessarily indicate most predictive tokens? Can one trust the explanation that is provided by the attention weights? Or to put it differently, is it possible for an adversary to manipulate these attention weights to be on the features that they want it to be and away from the actual predictive features? So to find this out, we set up our experimental tasks in such a way that we know certain features that are useful for predicting a certain task. And we measure a quantity called as attention mass on these tokens, which is simply the sum of attention probabilities on these tokens. And we try to manipulate this attention mass. So the way that we do is, we add a penalty term to the loss, which just takes away the attention from these predictive token, which we also call as impermissible tokens. So in a parallel work, the authors propose sort of a different kind of a penalty term that diverges the attention away from the original attention distribution. So this work is also featured in the poster session today. So for the suite of the tasks that we consider a bunch of classification tasks, and the highlighted tokens here are the tokens are the features such as race, gender, etc. that are useful for the prediction. And we also consider a bunch of sequence-to-sequence tasks. In these tasks, the The impermissible tokens, we get those tokens by using the gold alignments of the sequence-to-sequence tasks. So as you would notice that a lot of these tasks, like say bigram flipping, the gold alignments are implicit. So for instance, bigram flipping is the task of just swapping the adjacent tokens. So we know the goal alignments for them. But in the tasks such as machine translation, we get the goal alignments by a statistical tool called FastAlign. So once we have these goal alignments, we try to manipulate the attention on those alignments. The models that we use for our experiments are attention on embeddings, sequential models, and then self-attention based models. So more details can be read in the paper. Now we do a sanity check to find out if the features that we are taking away the attention from, are they even useful for predicting a particular task. So we consistently find out that the performance without these impermissible tokens, like the blue bar, is much worse than the green bar, which is with these tokens. So these tokens provide some value to the performance of the model. So now comes the interesting part, the results that we found. So in the occupation prediction task, here we show the different schemes of attention that we apply. So, so for instance, in the original non-manipulated naive attention, the attention mass on the leftmost blue bar, which basically shows the attention mass on the gender tokens that we found out to be predictive for this particular task, is quite high. But in the manipulated case, you would notice that there is almost no, so in the manipulated case, the attention mass on those gender tokens is very, very low. It's a very small positive value, and we are able to manipulate attention without any loss in accuracy. And we consistently find this across like the series of tasks that we do our experiment on. Even for machine translation, we see the same sort of trend with respect to the blue scores. So now we try to like go deeper into why does this happen. How are the models able to cheat and get around our like the circumvent our penalty term. The details are in the paper, but I will just go through I'll just go through an representative example. So in the bigram flip sequence-to-sequence task, this is the attention map that we get for non-manipulated training, and this is what is expected as well. But when we manipulate the attention mass away from the tokens that it should have been, we see like a very different attention mass. The attention mass seems to be shifted towards a few tokens towards the left. But when we try with a different seed and manipulate the attention, it shows like a completely different mask altogether. So the model seems to be using different kinds of workarounds for different seeds. So now we also want to find out if the human beings are actually fooled by the attention manipulation that we perform. We conduct a human study where we give humans input example and the corresponding predicted labels. So in the case of no manipulation, we find out that in 2 out of 3 cases, human beings think that gender tokens are like important for the prediction. So basically, the highlighted tokens in yellow are the ones represent the attention weights over the input example. In both kinds of penalty schemes, we find out that even though the model gives a good accuracy and it is using the gender tokens to identify the occupation of a person, but the human beings do not think that the prediction was influenced by the gender of an individual in none of the sentences. The second thing we try to find out is that, like, in the alternate attention maps that we provide by our manipulated attention, is it actually believable to actually have produced the predicted label? And we find out that although both the penalty schemes are deceptive, but our scheme is more believable. For instance, it focuses on tokens like medicine and specializes, which can actually which might actually lead to the predicted label being as physician. To conclude, in short, the conclusion is that the attention, if organically trained, we find out across a lot of different tasks that the value is high on the correct tokens that we expect it to be high on, but it is surprisingly easy to manipulate with negligible drop in accuracy, and with getting good accuracy even if the model is manipulated. Part of this work can be found on arXiv, and I will take, if there is any questions or discussions, I will be happy to take them in the poster session. Thank you.
Let's thank our speaker one more time and welcome the next one. Oops.
Yeah, that's nice. Mm-hmm. So it's just arrows, right?
Arrows?
When do we begin?
Yeah, sure.
Okay. Can I begin?
Yeah, go for it.
Hello, how are you? My name is Margarita, and in the next few minutes I will try to convince you that selection bias is an issue of first-rate importance in fairness applications. Let's go. So, algorithmic fairness is largely concerned with discriminatory decision-making that ensues from the use of any statistical prediction algorithms, including machine learning algorithms. A typical setup is when you have covariates, X, you have some target that you wish to predict, and you have a protected or sensitive attribute. You can think of this as gender, age, race, things like that. And so my criticism is that most of the work focuses on the later prediction stages of the decision-making pipeline, which includes data pre-processing, in-training, regularization, post-processing, and commonly ignores the crucial later and early stages of the machine learning pipeline. So I will particularly focus on the early stage, selection into the data set. So the claim is the following. Unfair selection is more than just another caveat to doing fairness, which is the way it is typically presented in otherwise excellent research. It can, in fact, thoroughly invalidate well-intentioned fairness interventions. So consider the following idea of an experiment. We will simulate a decision maker's fairness pipeline. Think of a hospital that predicts a diagnosis, say of asthma, for incoming patients. And they train a model on past patients' data. They are aware of fairness and they wish to satisfy some of the most salient fairness definitions. So they will check their predictions against some of the common fairness definitions, and then they will implement a fairness adjustment to satisfy those definitions. So one thing that they are not aware of is unfair admission into the hospital. So consider this generative process. What you need to know about this, A, you can think of as, for example, race. Y is the true status of having asthma, and notice that it is independent of race. And there are some symptoms that go to 11. And there's a selection mechanism that the hospital is not aware of. And so the interesting part is that there's this bias parameter that controls the odds of being selected into the training set that is dependent on your membership in a sensitive group. Which means that, for example, if you're black, you can think about it, your symptoms would have to be that much higher for you to even be in the through-the-door population of a hospital, which is not an implausible assumption considering the realities of highly racialized societies like the North American one. So the hospital observes the symptoms, builds a prediction of the disease status based on the symptoms and historical labels, and then they check it using the true value of the sensitive attribute. What they are not aware of is that their whole observation is only the selected. We chose the following definitions: statistical parity and equality of opportunity, primarily because these are the most salient ones. And so in the context of an 8-minute talk, what this tells you is she has the tables, she's legit. So for statistical parity, you can observe that in the population, there's actually no disparity when you're using a model trained using a single threshold for where you make your cutoff for who you will say is likely to have asthma and who is not. However, in the sample, you observe a lot of disparity, which makes you, the hospital, think that you might want to implement a fairness correction by using differential thresholds. So you will separate the two groups and you will move one of the thresholds lower until you satisfy statistical parity or equality of opportunity. Now, as you do that, you actually do fix the situation for false negatives in the sample, but that results in tremendous loss of fairness when the same decision rule is applied in the population. The same results hold for equality of opportunity. And if this example seems arbitrary, consider recent work by Ziad Obermeyer et al. In Science, where they actually found that this is more or less what is happening in actual hospitals in the US. For counterfactual fairness, the reasoning is quite similar. So say S is selection into the dataset, and the left-hand side causal graph is the ideal world in which selection is the only source of unfairness. So there's no causal path between the sensitive attribute and other covariates. So fairness only doesn't leak through other covariates. And however, if selection is ignored or unknown, then the data will be consistent with this causal graph on the right-hand side. And so while in the population, any predictor that is consistent with fairness through unawareness, in other words, which ignores the sensitive attribute, will be counterfactually fair. But a decision maker who does not observe selection will constrain their classifier to satisfy counterfactual fairness using the sensitive feature, which will result in unfairness in the population. So we find that fairness corrections in sample can lead to unfairness in the population. And the message is that differential base rates that even a well-intentioned decision maker observes, it's very hard to tell whether they are reflecting nature's generative process or they are an artifact of selection bias. So what are the solutions? We're interested in using causal inference to estimate the causal effect of the sensitive feature on selection. The simplest approach, of course, is to compare the sample proportions of A to the population proportions. Now, matching, or like in a randomized control trial, randomization takes care of any systematic differences other than in A. Matching could help compare individuals in different groups. You would do that if they have similar values of other covariates. However, standard methods of causal inference assume unconfoundedness. While that is not likely to hold in general, it's especially unlikely to hold in fairness settings. So what we're interested in is coming up with an approach that could potentially be robust to selection on unobservables, so unconfoundedness not holding. And that is perhaps the instrumental variables approach, or I will try to convince you that it is. The idea is the following. You want to come up with a variable that is causally upstream of the sensitive feature and affects selection, but only by way of the sensitive feature. So you will use an exogenous source of variation through that variable, and you will measure how selection varies with the portion of the variation in the sensitive feature that is attributable to this exogenous variation. And that gives you some kind of a handle, an estimate of the causal effect of the sensitive attribute on selection. There are several practical considerations, of course. So we're looking for something that is causally upstream of the sensitive feature. Now, instruments are notoriously difficult to come up with in general, and I think it's especially difficult to come up with in context of fairness, where what does it even mean to be causally upstream of an immutable characteristic, such as gender or race? Of course, we have to reconceptualize A, not to be race, gender, age, or what have you, but to be perceptions of those things, or to be the racist treatment, sexist treatment of an individual. Otherwise, we cannot use the instrumental variables. Now, fairness is hard, so most methods do rely on untestable assumptions. However, perhaps organizations have opportunities that maybe make them even better suited to use instrumental variables for fairness than researchers, because they can use something called encouragement designs, where the instrument is an encouragement to join the treatment group. So platforms like Facebook and what have you, they can easily conduct rich experiments where they build instruments. They do randomized encouragement via ads or emails, notifications, things like that, and have their own instrument. And so perhaps this presents an opportunity to do instrumental variables approach to estimate causal effects of sensitive features on the selection in the environments where it's of most crucial importance. So the takeaway message is that the pipeline, it shouldn't be an excuse, maybe it's an opportunity. Yeah, thanks.